Let us talk about turbulent flow. What is basically turbulence, and how we can measure them, or what are the approaches, or you can say views on them. Like there are two views. One is qualitative definition, and the other one is quantitative definition. So basically, qualitative, this word itself means how good or what quality, right? How good or quality. It basically states that if the value of the Reynolds number, right, in case of qualitative approach, how we can define turbulence, the term turbulence, right, that is basically the Reynolds number should be greater than 4,000. We all know that Reynolds did an experiment, and on based on that experiment, if the value of the Reynolds number is more than 4,000, we can say that this is a turbulent flow. But in case of the quantitative approach, right, that is quantitative approach, in case of this, or in case of quantitative view, you can already say that Re, the value of the Reynolds number, is basically the ratio of inertia force over the viscous force, right? So from here, we can see that if the inertia, right, if the inertia is very much greater than that of the viscous force, we can say that the value of the Reynolds number is basically very high, right? So in that case, we can see that as the Reynolds number is very high, so the flow is basically becoming turbulent in nature, right? So this is my quantitative approach, and based on the Reynolds experiment and the value of the Reynolds experiment, we can already say that that is my qualitative approach, right? All right. And now let's also define the Reynolds number. The Reynolds number is basically rho u L over mu, right? We already know that. I'm just telling it again. The Reynolds number, that is basically, if we just put those values, the inertia force and the viscous force is due to the viscosity, which is the internal resistance between the layers of the fluids when we apply a tangential force on that. Right. So that is basically rho u L over mu, right? And what are the I can say what are this? This is the density, this u is the velocity, this L is the characteristic length, and this mu is the dynamic viscosity. This mu is basically dynamic viscosity, right? And this L is nothing but characteristic length, right? This u is velocity, and this is basically your density. Okay, so we get this dimensionless number by just some observation, inertia force over the viscous force. All right, and we also know that this is dynamic viscosity. There is another type of viscosity that is called kinematic viscosity, and we denote them with this symbol, which is actually nu. And this nu is basically nothing but dynamic viscosity over the density. So if we now replace the value of nu mu in this equation of Reynolds number, what we end up getting is Re is basically UL over the dynamic viscosity. All right, so this is also an equation of the Reynolds number. So from here we can have some observations that if viscosity dominates, Re is less. So right from here we can see from this equation we can see from this equation also we can see that if viscosity dominates, Reynolds number is basically less, right? And if inertia dominates, what about if inertia dominates, inertia dominates, we get Re is very high, right? So these are things, and say there are some like numbers that you can also take a note, like REC. We can say that turbulence will occur. Okay, turbulence will basically occur when uh, turbulence will occur, or you can say turbulence will rise when Re, the value of the Reynolds number, is greater than that of the critical Reynolds number. So we can say, let me write that down also. That is also very important note, right? A turbulence rises, the value of the Reynolds number will be greater than Reynolds number critical, the critical Reynolds number, right? So we have like taken a note of this thing about this like condition. But what is this critical Reynolds number? So let us talk about that also. The critical Reynolds number is basically 2300 in case of like pipe flow, right? And this is also going to be the Reynolds number, critical Reynolds number. That can also be closely, approximately 5 times 10 to the power 5. In case of flat pipe boundary layer. Okay. Okay. So all with all of this informations in our like concern, we can say that we can also already define the turbulence based on that. The turbulence is an irregular. Basically, firstly, you can say that it is irregular, three-dimensional, and and time dependent, irregular, three-dimensional, and time dependent state of fluid motion characterized by the random fluctuations. That is a very important thing, random fluctuation. So you will see random fluctuations in case of the turbulent flows of the velocity and pressure. So random fluctuation of what? Of velocity, also of pressure. So we will see the equations of them. Okay, and strong mixing and a wide range of length and time scales. And we saw strong mixing some scales like length scale and time scale. So you'll also study about length scales and time scales. And okay, so these are some of the like words that define what basically our definition of turbulent can be. Uh, it's a uh, it's a subject, or you can say it's a topic where a lot of research is still going on. So for now, we can say that turbulent flow or turbulence is an irregular, three-dimensional, and time-dependent, it's a function of time, state of fluid motion, which is characterized by the random fluctuations of velocity and pressure. It also showcases strong mixing, and it has a wide range of length scale and time scale. So we are do not bother if we don't understand the things that we have just brought here. Maybe about the definition. We will also talk about the length scales, the time scales, also the fluctuations. In order to understand them in a more better way, let us draw a graph. Okay, that graph will like make it very easy. Also, let us write down a like the Reynolds number, critical Reynolds number. In case of flow past a sphere, we can write flow past sphere, the Reynolds number, or we can say the critical Reynolds number, that is approximately 5 times 10 to the power 5. So these are some of the informations that we can keep in our mind. Now let us go on and talk about a nice graph that will describe the turbulent flows and their natures. All right. So this is suppose the surface of a you can say this is a boundary, okay, boundary of a pipe flow, and this boundary can end somewhere here, like somewhere here it will end. Like if we take the cross section of that, then what we can see here is this that suppose from this direction you have the flow. Okay, this is the flow direction, and this is basically surface of a flat plate. Okay, what is this? Surface of a flat plate. All right. And we also have some nice things here that we are very interested to, we are going to look at it. These are those eddies. Okay. They are going to look something like this. Okay. So these circular things which are having a swirling motion, you can see. Uh, I don't know whether I have defined it in a perfect way or not. Like we can see those eddies here. These are the eddies. Okay. So this thing you can see over here, this is the eddy, and it has a characteristic length which is like this. This is its characteristic length L. Okay, so this is the eddy, and you can say this eddy, all of these eddies actually they are going to contain kinetic energy. They definitely have kinetic energy as they are like rotating and created by fast flow boundaries. Okay, so they are created by flow boundaries, and the size is basically L, is capital L in case of the integral scale. Okay, so integral scale. So what is this integral scale? I'm going to talk about them. I already told you that in case of defining turbulence, we have some lengths, wide range of lengths, sorry, scales. So this is one of the scales, okay, integral scale, okay. So we are going to be talking about the scales also, okay. All right. So this is the boundary surface of a flat plate. Okay. So along that surface, we have the eddies, which are quite large in, like you can say, size. Their characteristic length that is quite large. But as you move closer, as you go towards the center from the surface of the plate. Okay. So their shape changes. Like it will change into some other scale like this. It will change like this. Okay, so you can observe that its characteristic length, the eddies that I have drawn, they are basically eddies. The eddies that I have drawn with the green marker or the green pen, they are smaller compared to the eddies which are closer to the surface of the flat plate, which are created by basically the flow boundaries. Right, and as you move more closer, as you like move more closer, as you move more closer, you will see that the size of the eddies are getting smaller as you are going towards the center of the pipe. As you know that the center of the pipe will have the highest velocity, right? And here along this surface of the flat plate, it's actually uh, the velocity is very minimum. We know that from the mechanics already. All right, and now let's take a look at this. It's quite interesting to see. We are going to now define those things. At first, this big, or you can say the largest eddies, this region, we can say this is the larger eddy region. Okay, we are having the larger eddies, and after that we are having intermediate eddies, intermediate and after that we are having the small eddies. We can say, all right, small eddies. So Let us talk about that. And after the small eddies, we assume that those after those small eddies, there is no more eddies, and those eddies are actually transforming their energies, or you can say converting their energies into thermal energies or any other form of energies, and there is no more existence of the eddies. So this is according to the recent researches, but maybe we can do more research and find later that actually there are other kind of eddies. Like I'm comparing with the atoms. First, it was said that atoms has nothing, it cannot be broken. Then we found that atoms have electrons, protons, and neutrons, and also some uh, temporary, you can say, temporary entities, you can say, like boson, meson, things like that. So as of now, we don't know what are the things that after eddies, we're assuming that these eddies are actually transforming their energies into the some form of other energy, and there is no existence of the eddies. All right. So let us talk about this thing in a flowchart. It will be better. And one thing to be like clear here is this, that this is the surface of a flat plate. Okay. So this surface, along this surface, there is a like flow of this is the flow direction direction of the flow from this side to this side. As there is a flow, there are the formation of the eddies. Okay, so till now, just keep this in mind. Let us forget that there is any kind of pipe or not. Okay, for now, let us keep it like this to keep it simple. Okay, and then, or to keep it simple, or to keep it like more, acceptable. Okay, so now let's talk about the mean flow energy. This mean flow energy, due to the instabilities, okay, so there are large eddies. We already know that there are large eddies. Due to the inertia, okay, so they are becoming small eddies. You know that, okay, they are becoming small eddies, and then after the small eddies, okay, the viscous effect, or the viscous forces, due to the effect of the viscous forces, we are having thermal energies. As we can say that due to the viscous effect, the small eddies are disappearing. This small eddies, due to the viscous effect, you don't see any other eddies here. No eddies, or you can say no existence of the eddies. Why? Due to viscous effect. Viscous effect. In like one sense, we can say this also, that due to the viscous effect, due to the resistance, due to the friction of the layers, there is no eddies. Okay, and then we can like get some thermal energies, like the energy is being like converted like this. So this flow diagram is quite important. By this we can describe how things are working here, right? We can like very easily interpret these things, and we can also show off this diagram and also explain those things, that what is going on here. All right, so far we have talked about turbulent flow, qualitative approach or view or definition, and quantitative a definition. We talked about Reynolds number. We talked about the definition. This is basically the definition. This is my way of providing the definition. Like, and then let's talk about. We have talked about the eddy formations. We tried to explain it with the concept of eddies. Okay, what are the eddies? You can see here those this kind of circular. You can say those circular formations of flow. Okay, due to them closer to the boundary layer, they are having a very large size, whereas as we are like increasing the effect of inertia, they are getting smaller, and then we are not getting any more eddies. Okay, now we are going to talk about skills, as I promised that we will also talk about some skills that are very important and important to understand these things. So we'll be talking about integral skill. Okay, so this integral skill, that L, I told you the size of the large eddies, right? It is formed in the like largest. In this case, you saw this L size is L. I told you size is L. So what is this size L? We are trying to find that. Okay, so let us go through. So integral scale, this L is basically can be found with this expression. Okay, so this is the equation. So from 0 to infinite, we have to integrate this thing. So what is this R U U R? What is this thing? This is basically nothing but the longitudinal velocity at autocumulation. Okay, longitudinal velocity autocumulation. Okay, we can say that majority energy is being cascaded, and this is can be said that energy generation zone largest eddy in the turbulence, right? This zone is the largest eddy zone, right? This is the largest eddy zone, and energy cascade is being observed here. So we will also talk about that thing, energy cascade. What is that thing? Okay, in turbulent energy does not dissipate instantly. I'm talking about energy cascade. Okay. Okay, so as I was talking about integral scale, I already told you the formula, the longitudinal velocity autocumulation, and I'm now just shedding some light on energy cascade. Okay, so this is basically we can explain or derive it like this, that in turbulent flows, energy does not dissipate instantly. It passes from large eddies to smaller eddies, and then also to more smaller one eddies until it is finally dissipated. Okay, this step process is called energy cascade. So from this large eddies to the intermediate eddies to the small eddies, or maybe if there are more smaller eddies, the energy is not dissipating instantly. It's basically not instant process. Okay, it passes from large eddies to small, and then also to more smaller, and until it's finally dissipated. The eddies are finally dissipated due to what? Due to the viscous effect. Okay, this step process is called the energy cascade. So I can say that from this large eddies to the smaller eddies, there is a flow of energy, and that is not instant. It is not instant energy dissipation, right? It's not an instant energy dissipation. It is basically step process, right? So this process you will name this process as energy cascade. Okay, all right. Now, as we have already talked about the energy cascade, also this integral scale. What is this scale? These are some scales of turbulent flows. Okay, let me give the heading: scales of turbulent flows. Okay, so these are basically my scales of turbulent flows. I'm going to talk about them. So we have at first talked about integral scale. It is also denoted with L. Okay, this L is this. This scale represents the largest eddies and related to the conservation of velocity fluctuations. This is what? This is related to the conservation of conservation of velocity fluctuation. All right. And this RUR in bracket R, this is longitudinal velocity auto correlation, autocumulation. I'm just a little bit, I'll see this. What is this? Autocorrelation. This is autocorrelation. Okay. Please correct this. Okay. Energy production mainly occurs here. Okay. So we will also know about the energy production basically mainly occurs here. And roughly may call the size of the biggest turbulent eddies. Okay, we can say roughly that may call the size of the biggest turbulent eddies. Eddies. Okay, so we are done with integral scale represented by L, the formula, and some informations about this. Now let us talk about Taylor microscale, which is also very important. This is second type of scale. Let us name it one. Integral scale we have talked about, and now we are going to talk about Taylor microscale, and then we will talk about Kolmogorov microscale. Okay, so we are going to talk about Taylor microscale. It is represented with lambda. This represents an intermediate scale between large energy containing and small dissipative eddies. Its significance is that it defines the scale over which velocity gradient are significant but viscosity is not yet dominant. It means that this stage, the intermediate eddies, we are trying to uh, represent that thing. The okay here still the viscous effect hasn't become so violent like it became in case of the small or smaller eddies. So here still we are having some inertia effect, which is like little bit dominant over the viscous, or the viscous effect is not too much dominant or violent in this case also in case of the intermediate eddies. So it is basically the intermediate, you can say, stage representation, intermediate eddy representation, right? Here the velocity gradients are significant but the viscosity is not yet dominant. Here viscosity is not yet dominant, right? Velocity gradient is significant. Okay, and it's basically measuring the intermediate eddies, I can say, right? So mathematically, how I can define this is RUU and R is equal to 1 minus half R over lambda whole square. In this case, this lambda is equal to root over 15 nu. So yes, 15 nu over square and this sine. Okay, so this is my equation. We need to really keep this in our mind if we are looking to like solve numerical problems from here, from this like equation. Okay, so here we can, these are correlations basically. All right, they are basically nothing but correlations. Okay, and this what is this epsilon here? We are also going to talk about that thing. This epsilon is the rate of energy dissipation per unit mass. Energy per unit mass. Okay, so this is and this RUUR, that is the thing that I have already like defined here. And then we have another scale which is known as Kolmogorov. Sorry, this is basically Kolmogorov. Kolmogorov microscale is represented with this sign. Okay, and we are gonna like talk about those things. What is Kolmogorov microscale? This is basically, this is the smallest scale of the turbulence where the viscous effect is already taking over the inertia effect. As you are already seeing that in case of the surface of the flat plate, we are having the larger eddies, and then the energy dissipation is taking place. We are having the intermediate eddies and the smaller eddies. And after that, we are already having the viscous effect, which is already playing a dominant role. So due to that, we are getting thermal energies. This is basically energy dissipation. So if we look more forward, and if we want to represent those small or maybe the smaller eddies, we are going to take the help of the Kolmogorov microscale. So this is mathematically represented by a very simple formula. And we also need to know that at this scale, the value of the Reynolds number is very close to 1. The value of the Reynolds number will become very close to 1. And from dimensional analysis, we can already say, okay, so from dimensional analysis, this value of the Kolmogorov microscale, this is going to be equal to the dynamic viscosity. Sorry, this is the kinematic viscosity Q over the epsilon over this sign. Okay, so this is basically what I have already mentioned. This is the rate of the energy dissipation per unit mass. Okay, so if we do that, and this is going to be over 1 over 4. Okay, 1 over 4. So this is it. In this like Kolmogorov microscale, where we are analyzing this thing here, right? We are analyzing this thing here. Here, the viscous effect. This viscous effect is very higher than that of the turbulence. So, acha, viscous effect is very high. It means the turbulence will be very low. Okay. All right. So now we move forward, and we have defined the Kolmogorov microscale. Simply nu cube over the energy dissipation rate of energy dissipation per unit mass to the power 1 over 4. All right. This epsilon, I am saying again, this epsilon is dissipation per unit mass. And we have already seen that this is dynamic. This is kinematic viscosity represented by dynamic viscosity over the density, right? Okay. So eddy is smaller than this eta, or this eddy is smaller than this Kolmogorov microscale cannot exist. So we are like saying this thing. It's written in a book, but fundamental research is still going on this thing, whether there is any existence of smaller eddies than this Kolmogorov microscale. They are damped instantly by the viscosity. So I can write that with the reference that eddies smaller than Kolmogorov microscale cannot exist. They are damped instantly by the viscosity. Okay. So maybe you will be given the value of this kinematic viscosity and the value of this rate of energy dissipation per unit mass. And after by getting those two values, maybe the teacher can ask you to find the value of the like Kolmogorov microskeleton, right? So you can very easily do that by using this formula. Okay. In order to look at the derivation, how we have got those things, although it is from the dimensional analysis and these things, you can refer to books like Introduction to Turbulent Flows from Cambridge University Press. Okay. Now we will be looking at the relationship between the scales. Between the scales. So in case of this like larger eddies, we have studied about this scale L, integral scale. In case of the intermediate eddies, we had what? In case of the intermediate eddies, we had this lambda, which is Taylor microscale. In case of those small eddies, we had this Kolmogorov microscale. Right? There are like three scales for those three places. This L, this lambda, or this Kolmogorov microscale. And we also have discussed about the different formulas that are derived fundamentally or by the dimensional analysis. We can also use those things, like see, this is the integral scale, Taylor microscale, Kolmogorov microscale. Okay, and then we are going to derive the relationship between those things. So for large Re, for the large Reynolds number turbulence, okay, L by N, L over this L is the integral scale, this is the this eta like thing is the Kolmogorov microscale. They are proportional to Re, Reynolds number, to the power 3 over 4 over 4. Okay, and we can say the another relationship between these terms, lambda over this Kolmogorov microscale, that is basically proportional to Reynolds number 1 over 2. We know that as the Re will increase from this equation C increases, there is a wide range of eddy size. Range of eddy size. So the turbulence becomes richer and more complex. Okay, so from here you can see if my the value of RE will get increased, so we will get a wide range of the eddy sizes. So the turbulence will become more richer and more complex. So for today's class, that's it. We have mentioned a lot of things about turbulent flow, and we have at first talked about the qualitative definition, then we talked about the quantitative definition. Qualitative means the how good or how or what quality, right? We saw that RE, the value of RE, if it is greater than 4,000, we see that this is basically a like turbulent flow, or this is creating turbulence. And we also know that we have other flows like laminar flows, right? Laminar flow. Then we had like transitional flow, and then we had this turbulent flow, right? These are all obtained from the Reynolds experiment, where where he did an experiment with a pipe, and he injected dyes, right? We're talking about that experiment. And then we mentioned about the Reynolds number, RE, that is this equation. We defined this all. We talked about this. This thing is kinematic viscosity. Okay, this is actually basically the resistance to flow against the gravity. This is the dynamic viscosity, and this is the density. Okay, and then we just put the value of this thing on this equation, and then we got this equation. Okay, we talked about those RE, inertia force over viscous force. If inertia is very high, then the viscous force, the value of the Reynolds number is very high. Okay, if viscosity is dominating, your Reynolds number will be less. See from here, the viscosity is dominating here, as there is no eddies, we can see. So here the viscous effect is dominating, so there is no turbulence, or you can say the turbulence has been minimized or dissipated. The energies are no more there, so there is no turbulence, elimination of turbulence. Okay, and if the inertia will be dominating, the Reynolds number will be high. Here the inertia is dominating. In the larger eddy region, in this region, inertia dominating, we can say. So as inertia is dominating here, there will be larger eddies, and of course the Reynolds number is higher, so the turbulence is also very high. Okay. And then we talked about the definition, that is that it is irregular, three-dimensional, and time-dependent state of the fluid motion characterized by the random fluctuations of velocity and pressure. It showcases strong mixing lengths and a wide range of length scale and the time scale. So this can also be a way of defining like the turbulent flows. Then we moved on, and we talked about the critical values. We saw that the turbulence will rise when the value of the Reynolds number is greater than some critical value. So it will definitely depend on which case you are thinking about. So if it is a pipe flow on which actually Reynolds was like, although Reynolds was doing the experiment on a lab-based pipe, so this is the critical value in case of a pipe flow. If the Reynolds number, see, there is no dimension. Why? Because Reynolds number is a dimensionless number. So so the value will be close to 22300. So this is the Reynolds number, critical Reynolds number in this case. And in case of the flat pipe boundary layer, this BL means boundary layer. In this case, the value is 5 times 10 to the power 5. In case of the flow past a sphere, this is a sphere. There will be, if there is a flow past this kind of spheres, so the value of the Reynolds number is same as the flat pipe boundary layer, 5 times 10 to the power 5. Then we talked about this amazing graph. Like this is also like in one of the books, you can find it. Flow direction is from here. There are three zones basically. We have a larger eddy zone, a large eddy zone. Then we have intermediate eddy, and then we have small eddies, right? Three zones. Then we also saw how to characterize them or how to represent them using the different scales. In case of the larger eddy, we had inertia. We had integral scale. In case of the intermediate, we had the Taylor microscale. In case of the smaller eddies or small or smaller eddies, we had the Kolmogorov scale, right? We also talked about the energy cascade. Energy cascade. This is Like we are saying that when energy is being dissipated from the larger eddies to the smaller eddies, it's not instant. It's basically a step process which we can term as energy cascade. And then we saw that this thing here over here, this contains RKE. These are the eddies by which we are trying to understand turbulence. They are created by flow boundaries. Size is L, which is basically integral scale. In case of integral scale, it is L. In case of intermediate, this is Taylor microscale. In case of smaller eddies, this is basically Kolmogorov microscale. Then we talked about this flow chart, mean flow energy. Then there are instabilities. Due to the instabilities, we're getting large eddies. Due to inertia, getting smaller eddies, and the viscous effect is basically dissipating out all the eddies, and we are ending up getting some thermal energies. So basically, this is the conversion. Then we talked about the scales of the turbulent fluids, the scales of turbulent flows. Sorry, turbulent flow. There are three scales. Integral scale. This is the formula for integral scale. Then we had Taylor microscale lambda. This is the formula, and Kolmogorov microscale. This is the formula, and we also define the relationship between the scales. And we say that as R increases, so the wide range of eddy size will also will also be there, so the turbulence becomes richer and more complex. And eddies smaller than the Kolmogorov microscale cannot exist. We also say that by taking a reference from a book. Okay, thank you.